Hello YouTube, in this video I'm going to be talking about the ladder climber robot that I designed with my lab partner Gavin for my pneumatics and hydraulics class. Let's begin. So just like anything that I design, I have to start at the component level, and in this case the most important one would be the ladder itself. Sketching this is really easy. All you have to do is draw two squares, dimension them, and of course I went and measured the real ladder, so all of these dimensions are exactly the same. And this is going to be critical for the design of the actual robot. So the next step was to pick the components themselves and think about the action that the robot was going to take. My thought was to go the fastest. You want to be going from rung to rung to rung, just like a real person would, instead of going up to one rung and then having the other arm go up to the same rung and stop. Really, the fastest way is to be retracting while extending at the same time. And in order for that action to work, you actually have to have the travel length be longer than the rungs themselves. And in the case of the small cylinder, they're only 3 inches in travel. The big cylinders were 5 inches in travel. And the rungs are spaced out exactly 3 inches apart from each other. Now here are some of the original sketches that I made for the claw, and you can see that I decided to put the pivot point exactly horizontal to where the rung is. And the issue with that is, as the claw goes further up, in order for it to clear, it then has to rotate all the way down this way, and that creates a lot of extra distance. Okay, so here's the final claw and pivot design, and as you can see, I moved the pivot point pretty far up above where the rung actually is. And the reason why that is so as the claw is extending, it allows the rung to push the claw out of the way, and then as it clears above, the trajectory for it to rotate back over is pretty flat and doesn't create a whole lot of extra distance that the claw has to extend. Now the way that the claw actually extends back over is just by having a rubber band that goes across these 3 hooks right here. And the way that the pivot actually attaches to the cylinder is just from a 1/4-20 thread or a 1/4-28 thread that's built into the 3D printed part. Now over here, this little square is a rod guide, and that prevents the claw from rotating left and right as it's going up and down. Now the next part that I designed was the rod guides themselves. So the way that these work is they also have a built-in thread, and that threads on to the end of the cylinder. And as you can see, all it does is has a rectangle just a little bit bigger than the size of one of these square rods that we had. But what this also does is shortens the travel of the stroke as well for the cylinder. And that way it's not running all the way a whole bunch of unnecessary distance, and it's just going as far as it needs to actually go from rung to rung. Alright, so the next challenge is actually mounting the cylinders to the robot. So what I have here are these Vex robotics channels. To mount the cylinders to those, I made this clamp, and it's really simple. All it is just basically two semicircles, and they mount with an 832, and on the back side of that there's an 832 nut, and then there's 4 holes or 2 holes on either side, and that holds itself to the channel. Now the reed sensor has to go right here, so that's why there's a slot, because if you can see, this right here is the piston, and the reed sensor has to be right up against the cylinder in order for the magnet to trip. So that's why I created it like that. So it kind of doubles as a mount for the reed sensor as well. So the other thing that you have to do, or what I had to design, was this grabber. And the reason for that is because as the robot is climbing up the ladder, it's going to want to shift left and right because its center of gravity is changing. So the whole point of the grabbers is to actually prevent the whole robot from rotating. Now, what I had to design here is basically a slide, and also it has a roller, and you can't see it because I didn't put the screws, but this is also held in by a rubber band. And the reason for that is because the ladder wasn't actually perfectly square. So when it's at the bottom, it can start all the way in, and then as it climbs up the ladder, the grabbers can separate while still maintaining traction onto the side of the ladder. The other trick about this was that we weren't allowed to grab around the entire ladder, so we could only touch the outside face. So what I ended up doing with the roller is I got these little like silicone rubber band things, and they basically acted like tires. So this thing is squeezing the sides of the ladder, and then it's also with the tires preventing it to fall backwards off of it. Now the last thing that I designed, and it wasn't entirely necessary, was having this DCV mount. Now it definitely helped a lot with structural integrity, because otherwise it would have literally just been the cylinders and the cylinder mounts that are holding the two channels together. So it doubled as a mount for the DCV and also structural integrity. Now my thought behind this was I wanted to keep all of the lines together, so everyone else was having their DCVs on the table, and then they would have to run 4 tubes to each cylinder, whereas mine, you would just have to run one air line and then one cable to power the DCVs. And I thought that was a lot neater. It does create a little bit more weight, but I thought it would be less weight with the tubes and the cables dangling off.
Yeah, just okay.
So it warped because I went twice on one.
Oh, okay. Yeah. All right.
So here are the first test runs of the robot on the ladder. For these first runs, it's actually manually button operated. We would later need to actually automate it using something called Fluid Sim and an Easy Port, but for just the test runs, it's good to do this manually just so nothing gets screwed up. But you can actually see it kind of falls down a little bit because my partner Gavin misclicks and kind of presses it too early and causes the robot to go a little bit crooked. The nice thing about automating it is, since we have 4 reed sensors on it, it will make sure that it will complete the whole travel movement before extending the next cylinder. That way it won't fall down like it did in this video. The other part of the automation requirement is that we can't actually intervene in any way, so we only have a start button and then an emergency stop button. The robot has to automatically stop itself, so it has to count the rungs as it goes up, and then once it gets to the top, stop on its own. Here's Gavin's program that he made in Fluid Sim. It's basically a series of relays and switches with 2 timers and a counter. When the program is started, it fires the first cylinder on the right, and then it starts to retract when the reed sensor on the top is detected. Once the first movement is finished, the cylinders start to alternate, and they only fire when the reed sensor on opposing sides are tripped by the cylinder completing their movement. There is also a slight delay added for when the cylinder reaches its extension, making sure the other cylinder has fully retracted so it doesn't skip the rung. We started this process by going slow and watching what was happening. Once we got it working, we adjusted the throttle valve so that the cylinders could move faster. We also decreased the delay so that there was less time with no motion. It got to a point where the cylinders were actually pulling the robot so fast it was causing it to jump. And we decided to name it J Garbanzo after a jumping bean because it has this characteristic little hop that it did when it goes from rung to rung. After all the tuning was complete, we managed to climb the ladder in a little over 2.5 seconds, which was the fastest in the class. Okay, so what would have I done differently about the design? The only thing that I'd really change is I'd flip the directions of these channels so that the U would be facing inwards towards the ladder instead of away. And the reason why it was designed this way was, for one, I wanted the cylinders to have their center of gravity to be as close as possible to the ladder. So that meant having this cut out of the channel. But the problem was it was pretty difficult to do that, and it did really make it so that it was totally relying on this 3D printed part for its structural integrity there, and it made it kind of floppy, and I wasn't expecting how difficult it would be to actually cut it, and it kind of ended up bending up the channels a lot because we only had hacksaws, so this cutout was unnecessary and it could have just been facing the other way. All in all, this was a really fun project to work on. I've never done anything with pneumatics or anything with this much mechanical action, so it was a good exercise for me since most things that I design are static. It was nice to work in a team effort and to be able to play to my strengths, although I'm hoping for next semester I'll be able to spend some more time learning how to program. If you made it this far into the video, thanks for watching!